The origins of World War II fighter engines lie in a period of urgency and uncertainty, when aviation engineers across the world understood that the next major war would be decided not by endurance flights or record-breaking speed runs, but by sustained, violent combat in the air. By the mid-1930s, it had become clear that the engine was no longer just a component of the aircraft. It was the aircraft. Airframe designers could refine wings and reduce drag, but without a decisive leap in engine performance, fighters would remain trapped by the limits of the previous decade. This realization triggered an unprecedented acceleration in piston engine development, driven by fear, ambition, and looming war. Britain's position was uniquely precarious, anticipating a defensive air war over its own territory. British planners demanded an engine that could deliver consistent power, climb rapidly to interception altitude, and survive prolonged high-output operation. The result was the Rolls-Royce Merlin, an inline, liquid-cooled V12 that prioritized compactness, adaptability, and mass production. From its earliest versions, the Merlin was designed not as a finished product, but as a platform for constant improvement. Engineers accepted that the engine entering service would be obsolete within months, and they built it accordingly. This philosophy, continuous refinement under combat pressure, would become one of Britain's greatest advantages. Germany approached the problem from a different angle, seeking technical superiority through precision engineering. German designers focused on efficiency and pilot advantage in combat maneuvering. The Daimler-Benz DB6-1 embodied this mindset. Its use of direct fuel injection allowed German fighters to perform negative G maneuvers without engine starvation, a critical edge in early dogfights. The DB6-1 also emphasized smooth power delivery and high-altitude performance, aligning with German expectations of short, decisive air campaigns. However, this complexity came at a cost. Production difficulty and sensitivity to fuel quality would later become serious liabilities. Across the Atlantic, the United States entered the late 1930s without the same sense of immediate threat. American engine development favored reliability, standardization, and industrial scalability. The Allison V1710 reflected this cautious approach, well built and dependable, but initially lacking the high-altitude supercharging needed for European air combat. This was not a failure of engineering, but of doctrine. The United States expected its fighters to operate differently, and only combat experience would force rapid changes. When that shift came, American industry proved capable of adapting at enormous scale. Japan's engine development was shaped by geography and limited resources. Operating across vast ocean distances, Japanese planners demanded engines that were light, fuel-efficient, and capable of long range. Weight saving became a dominant design principle. Armor protection and self-sealing fuel tanks were often sacrificed to reduce mass and extend endurance. Engines like the Nakajima Sakai were not underpowered for their time, but they were pushed close to their structural limits. Early war success masked long-term vulnerability, as these engines left little margin for increased power or improved survivability. Underlying all these national approaches was a shared technological revolution. Supercharging emerged as the single most important advancement of the era. By forcing more air into the engine at altitude, superchargers allowed fighters to retain power where older engines would suffocate. Metallurgy advanced rapidly, with new alloys enabling higher temperatures and greater stress tolerance. Fuel chemistry evolved in parallel, producing higher octane aviation fuels that allowed increased compression ratios without destructive detonation. Each improvement unlocked another, creating a feedback loop of escalating performance. Yet these engines were not born reliable. Early combat revealed brutal weaknesses. Overheating, oil leaks, and catastrophic mechanical failures were common. Ground crews became as vital as pilots, learning through trial, error, and loss how to keep engines alive under combat conditions. Maintenance schedules shortened, spare parts were cannibalized, and field modifications became routine. The engine war was fought not only in factories, but on muddy airstrips and improvised hangars close to the front. As World War II intensified, fighter engine design became a ruthless contest where marginal gains translated directly into survival. Every major power discovered that the limits of air combat were no longer set by airframes or pilot skill alone, but by how much stress an engine could endure before tearing itself apart. Engineers were forced to extract unprecedented power from piston engines that were already operating near the boundaries of known physics. What followed was an era of extreme engineering, where engines became both marvels of innovation and fragile instruments of war. Two competing philosophies dominated the conflict. Inline liquid-cooled engines offered reduced frontal area, enabling higher speeds and cleaner aerodynamics. Radial air-cooled engines, by contrast, embraced brute force and survivability, accepting drag in exchange for resilience. Neither approach was universally superior. Each shaped the fighters built around it and the tactics those aircraft employed. The war demonstrated that engine design was inseparable from national strategy. Britain relentlessly refined the Rolls-Royce Merlin, transforming it from a capable early war engine into a high-altitude powerhouse. The key was supercharging. Single-stage superchargers soon gave way to two-stage, two-speed systems that allowed fighters to retain power at extreme altitudes. This gave British and later American fighters the ability to intercept bombers, where earlier engines would have suffocated. These improvements demanded stronger crankshafts, improved cooling jackets, and increasingly precise manufacturing tolerances. The Merlin's evolution was not smooth. Boost pressures rose, engine lives shortened, and maintenance demands exploded. But its adaptability proved decisive. Germany pursued refinement through mechanical sophistication. Engines such as the Daimler-Benz DB series relied on fuel injection rather than carburetors, granting consistent performance during violent maneuvers. German engineers focused heavily on altitude performance and efficient power delivery, believing speed and climb rate would offset numerical inferiority. However, as power outputs increased, German engines became increasingly sensitive to fuel quality and maintenance discipline. Late war variants delivered impressive figures, but often at the cost of reduced service life. Some engines were effectively disposable, expected to last only a few dozen combat hours before replacement. An assumption Germany's shrinking industrial base could not sustain. The United States approached the problem from a position of industrial abundance. American designers favored engines that could absorb damage, operate for long hours, and be produced in staggering numbers. The Pratt & Whitney R12800 radial engine embodied this philosophy. Massive, powerful, and remarkably robust, it could continue running even after sustaining severe combat damage. Its size allowed for generous cooling margins and heavy internal components, making it ideal for prolonged operations over ocean and jungle. While less elegant than some inline engines, its reliability became a strategic weapon in itself. Radial engines also proved forgiving in combat. Air-cooled cylinders could tolerate bullet damage that would instantly disable a liquid-cooled system. This resilience shaped pilot confidence and operational doctrine, particularly in the Pacific, where fighters operated far from friendly bases. However, radials introduced aerodynamic penalties, requiring careful cowling design and cooling flap management. Engineers responded with increasingly refined airflow control, reducing drag while maintaining adequate cooling, a delicate balance that demanded constant attention from pilots. Fuel chemistry became another decisive factor. Higher octane fuels allowed engines to run at increased boost pressures without destructive detonation. Allied access to superior fuel stocks enabled higher power settings for longer periods, directly translating into better climb rates and top speeds. Engines were no longer limited by mechanical design alone, but by what the fuel could tolerate. In many cases, a change in fuel specification unlocked performance gains without altering the engine's physical structure. As power outputs rose, engines generated enormous heat. Cooling systems became increasingly complex, with radiators, oil coolers, and airflow channels carefully integrated into the aircraft's design. A slight miscalculation could lead to overheating, seizure, or fire. Pilots were trained to manage throttle mixture and radiator settings constantly, especially during climb and combat. Engine management became an art, demanding discipline under extreme stress. Maintenance demands grew just as rapidly. Engines required frequent inspections, part replacements, and meticulous care. Ground crews operated under relentless pressure, often working through the night to keep fighters operational. In harsh climates, Arctic cold, desert heat, tropical humidity, engines behaved unpredictably. Oils thickened, seals failed, corrosion spread. The theoretical performance of an engine meant little if it could not be kept running at the front. By the middle years of World War II, it had become undeniable that fighter engines were shaping the very geography of the war. Where an aircraft could fly, how long it could remain there, and whether it could return at all depended on the behavior of its power plant under combat conditions. Engines no longer served simply as sources of propulsion. They dictated strategy, logistics, and operational reach. Entire air campaigns rose or collapsed based on whether engines could deliver reliable power day after day under the strain of total war. In Europe, the struggle for air superiority over occupied territory exposed the brutal demands placed on fighter engines. Long-range escort missions pushed engines far beyond what their designers had originally envisioned. Fighters had to cruise economically for hours, then suddenly deliver full power at altitude during combat, often while damaged. The arrival of drop tanks extended range, but they also increased engine workload and thermal stress. The success of deep penetration escort missions depended on engines that could tolerate prolonged high-altitude operation without catastrophic failure. This requirement reshaped Allied fighter deployment and directly influenced the collapse of enemy bomber interception efforts. On the Eastern Front, the challenge was survival itself. Engines had to start in sub-zero temperatures, operate from primitive airfields, and withstand dirt ice and poor fuel quality. Soviet and German fighters alike suffered massive non-combat losses due to mechanical failure. Ground crews lit fires beneath engines, drained oil nightly, and improvised repairs with limited tools. An engine that could tolerate abuse often proved more valuable than one with superior theoretical performance. In these conditions, reliability became a form of combat power. The Pacific theater imposed a different tyranny. Vast distances meant that engine endurance equaled pilot survival. Fighters operating over open ocean had no margin for failure, A single mechanical issue could mean disappearance without trace. Engines had to perform flawlessly in heat, humidity, and salt-laden air that corroded components and degraded lubricants. American industry's emphasis on durability paid dividends here, allowing sustained operations from island bases and aircraft carriers. Japanese engines, optimized for lightness and range, delivered impressive early results, but struggled to absorb damage or tolerate prolonged wear as the war dragged on. As the conflict escalated, late war engines reached astonishing output levels. Emergency power settings allowed brief surges of performance at the cost of engine life. Pilots were warned that using these settings could destroy their engines, yet in combat the choice was simple: mechanical survival or human survival. Many engines never reached their intended service hours, dying violently in the air or limping back to base trailing smoke and oil. Fighters became expendable platforms for engines pushed beyond rational limits. Industrial capacity increasingly determined outcomes. The Allies could afford engines that required frequent overhaul because they possessed the factories, materials, and trained labor to sustain replacement. The Axis powers, especially Germany, faced mounting shortages. Late war German engines delivered impressive performance figures, but often at the cost of reliability and longevity. Some were rated for operational lives measured in mere dozens of hours. In theory, this was acceptable in a short war. In reality, it proved disastrous in a prolonged conflict. Maintenance became a frontline activity. Ground crews worked under fire in mud, snow, and heat, racing to keep engines operational. Every sortie depended on their skill. A pilot might claim a victory, but it was the engine crew that made the mission possible. Training manuals grew thicker, procedures more complex, and spare parts more critical. Engines that could be maintained quickly and predictably multiplied combat effectiveness far beyond their raw performance figures. By 1945, piston engines had reached their absolute peak. Power outputs had doubled, fuel consumption soared, and tolerances tightened to razor margins. The engines that had carried fighters through the war were worn out, overstressed, and nearing the end of their evolutionary path. Jet propulsion was already emerging, not because piston engines had failed, but because they had succeeded too well, pushed so far that no further gains could be extracted without unacceptable cost.